Alright, today we're going to talk about the distance formula. So I'm going to review something that's not going to seem completely obvious at first why we're reviewing this. But it's very important for the distance formula. The Pythagorean theorem. What does the Pythagorean theorem say? It says if you have a right triangle which has two legs, A and B, and a hypotenuse, C, then A squared plus B squared equals C squared. So if I had the triangle with sides 12 and 16, and then I didn't know this side, I could find this side by just taking 12 squared plus 16 squared equals C squared. Then I have to compute this, so 12 squared is 144, 16 squared is going to be 16 times 16, which is 6 times 6 is 36, 6 times 1 plus 3 is 9, 16, 6, 5, 256 equals C squared. And that makes sense because this is a power of 2. Then we add those together, and we get 400 equals C squared. So C is the square root of 400, which is, what is the square root of 400? It's just 20, right? 20 times 20 equals 400. And so you can find that C must be 20 in this triangle, using the Pythagorean theorem. You can also find the legs by plugging in C and A or whatever. You can find B. So it's a really useful theorem for right triangles. But it actually is way more useful than just in right triangles. And the distance formula is one reason why. So we're going to kind of extend the Pythagorean theorem today, using what you now know about radicals in a slightly different way. So let's say I have a coordinate plane. And let's say I have a point right here. Maybe this is 1, 1. And then let's say I have another point. I'm going to write that in this. I have another point up here. Maybe that's, I don't know, like 3, 4, or something like that. The distance formula, the idea behind the distance formula is to find how far it is from this point to this point. And there's a law that says the shortest distance between 2 points will always be a straight line. Okay? Which makes sense kind of intuitively, right? The shortest distance isn't going to be like this curve or something. The shortest distance will always be a straight line connecting those 2 points. So what we're really trying to figure out is what is the length of this line. That's what the distance formula is trying to tell us. How far from here to here, how long is this line that connects these 2 points? How could you find that out? What would you do? Do you have an idea? Okay.
Equals the square root of
Close. Okay. Something with x's.
And then it's squared.
Uh-huh.
And then this plus parentheses y.
Same with y squared. Does this look familiar at all? The square root of the sum of two squares. Think about when we just found the length of this side of the triangle, right? C. What we did was we had like 3 squared plus 4 squared equals c squared. And we didn't exactly do it this way, but eventually we took the square root of both sides, right? We had the square root of 3 squared plus, or we had whatever, 12 and 16 or whatever. So there's some parallelism here. This is the square root of one thing squared plus another thing squared. The distance from is going to be the same sort of a thing, right? This squared plus this squared all under a square root. So where do you think it might come from? Is there a triangle on here somewhere? Is there a triangle? Let's try to think about this. We know the distance from here to here, right? You know how far it is from 1 to 3. That's fairly easy just to count. And we also know the distance from here up to here, right? That's just from 1, y being 1, up to y being 4. So would you agree that this is the same as this? The distance from this, the y coordinate to this y coordinate, is the same over here. And that's where our triangle comes from. What we're doing is we're looking at how far is it from this x to this x, and then from this y to this y, and we're making that into a triangle. And it's going to be a right triangle because this line is horizontal perfectly, and this line is vertical perfectly. So does anyone want to try to guess what the x's are going to be? We know that in some way we're not using the Pythagorean theorem. We're trying to find this side, the distance. So let's call that d. We need this side. What is the length from here to here? 3. So we start at 1, right? And we go to 3. So the distance would be, the length of this segment would be just 2, right? We go 1, 2. So this side is 2. And this side would be how much? From 1 to 4 is 1, 2, 3. 1, 2, 3. So this side is 3. So now we could find this. I mean, if I just gave you this triangle, right? And I said, find this side over here. I'm going to call it D. This side is 2 and this side is 3. You could find that. What would you do? 2 squared plus 3 squared equals D squared. 4 plus 9 equals square root of 4 plus 9 equals D. So D is the square root of 13. It's not a great number, but it's a number. And that's the same thing for this. So now we know that distance from this point to this point is the square root of 13. All right. So where does this all kind of come from? How do we generalize this? What is the distance? All right. So let's take another starting point. let's say that we start at 0, 0. And then let's say the point that we want to go to is 3, 4. Just up at that point. Our distance is going to be, the shortest distance is just a straight straight line that connects those 2 points. Right? And we can find that distance using the Pythagorean theorem and figuring out this length and this length. So let's make those dotted lines. Even though this one's on the axis. I'll kind of make it dotted. So what is this length here? From 0 out to 3, the length of that is, let's redraw our triangle over here. Length of that is 3. So this side is 3. The length of this side, from 0 all the way up to 4, is 4. So what is our distance, our missing side here? 3 squared plus 4 squared equals b squared. So we're going to take the square root. We have the square root of 9 plus 16, which equals the square root of 25. What is the square root of 25? Oh, it's 5. So we know our distance here is 5. Yeah.
Would it be plus x1?
Yeah, so now let's go back and look at this formula that Graham sort of remembered. How did we figure out that the length of this side was 3? And how do we figure out the length of this side was 4? How do we know that? Or going back to our other graph, how did we know, right, that the length of one side was, I don't even remember what it was now, 2, and the other side was 3, right? I think our points were like 1, 1, and the other one must have been 3, 4. How do we figure out that this was 2 and this was 3, or that this was 3 and this was 4? Is there a generalized way that we could say that? Like, let's say I gave you a graph, and I said, here's a point, but I'm not telling you what values they are. This is just going to be x1, y1. And here's another point. This one's going to just be x2, y2. You don't know what numbers x and y are. I'm not going to tell you. This could be like 1, 5, but maybe it's 1, 4. And this one looks higher, so it could be like 6, 8, but maybe it's like 7, 8. How would you find the distance between those 2 points, x1, y1, and x2, y2? We can use that same process. So we can figure out the length of this side of the triangle and the length of this side of the triangle. But how are we going to express the length of this side? What is the length of this side? Yeah, so we're going to have to subtract something. What are we subtracting from what? To find this side of the triangle. Okay, so let's think about that. x1 minus x2. If you go back to here, what you're saying is 1 minus 3, right? 1 minus 3. Is that how we got this? Not quite, because 1 minus 3 would be negative 2. You're super close. But to find the distance from here to here, or the length of this side of the triangle, we know this is x1 and this is x2. It's not x1 minus x2. It is x2 minus x1. And actually it doesn't matter. You could do it either way. But it's just kind of more intuitive to think of it as x2 minus x1. That is the distance from here to here. So think about it. Up here we had 3, that's x2, minus 0. Over here we had 3 minus 1, that is 2. x2 minus x1 is the side of the triangle. What is the other side of the triangle? Up here. y2 minus y1. You could also write this as x1 minus x2 squared plus y1 minus y2. It doesn't matter. And the reason I say that is sometimes your y's or x's will be negative numbers. And it might actually make more sense to think of it that way. But for now, let's just think of it as this one. So what we have is this side of the triangle. Right? And this whole thing is this side of the triangle. So we're squaring those, and then we're taking the square root just as if this were the Pythagorean theorem. So you have a couple options now. You could memorize this formula. Distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Or you could just remember that the distance between 2 points is the hypotenuse of a right triangle. And then you don't really have to memorize it. You can kind of go back and figure it out. Right? So let's do some examples using this one. What is the distance between 7, 3 and negative 1, negative 4. Let's say I gave you these 2 points and I said, what's the distance between? You don't have to draw a graph, but you can. So 7, 3 is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. Right about there. Negative 1, negative 4. So we want to know this distance. That straight line that connects those two points. We need to know this length, and we need to know this length. This length here, the x length, the change in x, is another way of thinking about that. So the change in x is 7 minus negative 1. 7 minus negative 1, which is 8. And the change in y is, from here to here, 3 minus negative 4, which is 7. So the length of this side is 7, the length of this side is 8. Okay. How do I find this side? Oh, 8 squared plus 7 squared equals my last side squared. Take the square root. So my distance is going to be the square root of 8 squared is 64. 7 squared is 49. 64 plus 49 is What is that, like 113? 113. Does that have any perfect squares in it? There's no 3s, no 2s. Are there any 7s? I don't know. 7 goes into 11 once. 4, 43, no. So it might just be that, square root of 113. So it looks, it might even be prime.
And so that's the answer?
So that's your answer, right? This length is 113. But this is when you need to go back to your radical tricks that we've been learning. If you can simplify this, you would simplify it. Right? In this case, we can't. I don't think. All right. So I'm just finding this side and this side, adding them and taking the square root. Let's see if we can do one without drawing the graph. No graph. So let's try this one. The distance between 3, negative 5 and negative 3, 0. What is the distance? So, change in x. When have you heard change in x before? Haven't you done this before? Yeah, why would we talk about change in x when graphing things? Change in x, change in y.
Slope?
Yeah, that's the slope formula, right? And if you think about it, this is fairly related to the slope. It's just that we don't care about the ratio between them. So when we're figuring out the slope of a line, we did the same thing, right? The slope is like this divided by this. Change in y over change in x. So that's the same. We're still kind of drawing a triangle when we're figuring out the slope. So you've done change in y, change in x a lot, actually. And if you think of the distance formula as being the square root of change in x squared plus change in y squared, it might make it easier, I don't know. Just because you've seen that before. So what is change in x? Well, we take one of these minus the other one. So let's do, I'm going to call this one x2, y2, and I'm going to call this one x1, y1. I just think it's going to make the subtraction a little easier. So I want to do x2, 3, minus x1, which is negative 3. And then I want to do y2, which is negative 5, minus y1, which is 0. What is 3 minus negative 3? 3 plus 3, which is 6. What is negative 5 minus 0? Negative. Anything minus 0. Okay. The signs don't matter because we're about to square these. So if you wanted to flip this around, you could. Like you could do 0 minus negative 5 and get 5. And it's not going to affect your answer because negative 5 squared is 25 and 5 squared. So you can kind of ignore your signs here, which is kind of nice. Let's plug these into our formula. The square root, so distance equals the square root, x2 minus x1 is 6 squared, plus y2 minus y1, I'm just going to say 5 squared, because I know that the negative's going away. I'm squaring it. So my distance is the square root of 36 plus 25, the square root of 1161. Does that have any perfect squares in it? I don't think so. So that's our answer, the square root of 16. And that's it. So you can do this without drawing a graph. I think on your homework that's probably going to be a good idea. You might even just write out the whole equation. So let's do one more example. The way that I sort of thought about this was as two sides of a triangle, but you could also just do it like this. 6 comma negative 7, and 3 comma negative 9. The distance between those 2 points, I'm just going to plug it into my distance formula. So let's call this x1, y1, x2, y2. The distance equals the square root. So I'm just going to do x2, 3, minus x1, 6 squared, plus y2 is negative 5, minus y1 is negative 7 squared, and then I just solve that. It looks kind of complicated, but it's really not, because all we have to worry about is the number. 3 minus 6 squared, that's negative 3 squared, which is just 9. And then negative 5 minus a negative 7, that's negative 5 plus 7, which is 2 squared, which is 4. So we have the square root of 9 plus 4, or the square root of 15. And that's your answer. It can't be simplified in that case. D equals the square root of 15. Alright, any questions about this? Plugging in the numbers. So I wanted to show you where that came from before we did too many examples.